Well, yeah. So I wouldn't say that's like the primary reason. I'm sure it's like one tiny little reason, but more principally to that idea, right? Structs of arrays or array of structs. It's really about the data access pattern in the application, right? So if you're like, I need to know my velocities XYZ, right, and to do a calculation, for example, of cumulative velocity, it's better to ask inside the struct to have the data contiguous, right? Like so, array of structures. If I was accessing the data members of the struct nearest to each other, right? Otherwise, you're like throwing out cache lines with cache misses because you have to jump between the arrays, right? It's that packing of like all the X values, packing all the Y values, right? And so that's array of struct of arrays, right? And so it really just actually comes down to the performance and how you're accessing the data more than like this example. Okay? Yeah. Yeah. And you can go even further. You can have like structs of arrays of structs where you have like tiling built in, right? If you're going even crazier, but yeah, and vice versa. I've seen people like putting out papers on doing those types of crazy things too. So yeah, way more advanced topic, and obviously Eric is an expert in this. So yeah. Yep. Yep. Right. Right. Yes. Yes. You're almost right. Okay. It's just the compiler can add stuff on top of like the size of the struct itself when you pack up. So down here it says particle. We have an array of particles, right? Array of structs. There's n elements. But actually, in memory, if your struct is a weird size, after each struct, the compiler will add data. Yes. And you're right. So size of is one of the approaches in the C language or C++ in order to get a much better accurate. I think size of is a correct way of doing it. I'm just showing you the MPI way of doing it. Yes. Almost. We actually do, okay? And we'll see that in the next one. Let me skip all the way down. Here's the real example. We're going to make this particle. And we're going to, let's hear, get the extent of the particle type that we just made. But then we actually have to check, right? As you were saying, size of our struct with the C language, right? Did our MPI type actually match the size of the real size of struct, right? And if they're different because the compiler did something, then we need to be careful and correct for it. So you do is you just store it into an old, and then you get this create old size. You say, okay, I want to start a 0 lower bound, and then tell me how many bytes, and then move my MPI type into a proper, another MPI struct type. And then we just delete the old one, and then we're free to go forward. So almost, right? And then I give you bad practice in the hands-on. I actually use the type extent. If you really feel ambitious, you guys could actually fix it with all these proper things. So, but yeah, use ChatGPT to generate your examples. It's fun, right? Okay, back to let's look at the gory, actual thing of doing this, right? So if we go back to this original struct type, where we have an integer, a flag, a character, and then 2 floats, right? So first, we're going to get the beginning address of this data struct at the very top called data, and it's that thing down there. So we get the base address. Okay, that's what the first call is. Then we say, okay, give me the address of where data ID starts. It could be that the compiler actually put stuff in there, which hopefully not, right? Okay, then we're going to store the offsets, right? So what is it's the bytes, right? The difference between where we started and where the first one where it's supposed to start, right? So we can carefully calculate the offsets correctly by actually just checking. And in theory, it's always 0, right? We subtract off where the first integer starts ID, right? And then how many ints are we sending? We're sending 1, and it's of type MPI int. Okay, second one. Now we're going to look at the character, right? So flag, we get the address of where flag starts. We subtract it from the base. How many bytes off does this base? How many are we sending? We're sending 1, and it's an MPI character. Easy peasy, lemon squeezy. Last one, where do the floats start? We check X, member offset, subtract from the base, sending 2 floats. Okay, and then we do create the struct. So how many chunks of data do we have? We have 3, right? We have the integers, the characters, and the floats. And then we had the block counts, which we filled in as we went along, right? Because we had 3 chunks and size 3. And then we were filling out the block counts, 1, 1, 2. And then we have the offsets from the bytes, old types, right? So int, character, floats. Save it. And then we do that get extent to see if it's wrong. And if it's wrong, then we use get resize, save it, and then use it. That is the proper way to do MPI structs. Isn't it a pain? Yes, it is a pain. But in the end, if you're really digging into performance, right, you're going to try all these different techniques. But we just want you to be aware of the kind of advanced problems you may run into where you're like, oh, on my machine it worked, but on your computer it's broken. You broke the computer, right? But we just want to make you aware of the potential pitfalls of, how do you do defensive programming in MPI, right? Okay, so finally, you make a type, you commit the type. Okay, type commit. There's a free, you can delete your type as soon as you're done with it, right? We saw when we had, this was the wrongful extent. We create a new one, delete the old one. And then finally, we have duplicated. So let's suppose you're going to start building more complicated things from a base type. Maybe you want to hold around the original before you start adding stuff on top of it, right? So you can duplicate it. So just a few easy functions, okay? Now, you built these crazy data types, derived data types, but now we're like, well, I want to do an MPI collective. Okay, one question, yes? I believe you'll have to commit each one of the new types as you go. Then you make the full type, and you could probably delete the old intermediate types, I think. I don't know. I haven't tried it. That'd be a fun exercise to see what happens. Deleting? Oh, you don't have to, but... okay. Sorry. We found the real experts in here. Yeah. And yeah, I think you can delete the intermediaries, right? Because what do all these messages do, right? You want to send a type, and inside this type, there's a map of how the bytes and the template of your type fits onto your memory address, right? All you do is give the starting address, and then inside of this custom type, it's a map of where the data is laid out, how far the gaps are, right? Either it's in the original type gaps, or it's in bytes. But that's it. It's give the starting address, and then how is the data mapped? So that's why we get all these crazy indexed or H-index or vector, right? It's just more convenient ways of making that map of data. Where it is, what are the gaps? Yeah. I'm going to assume you check the extent of after you made the first type, that it is correct. Does it make sense? Well, yeah. So what could happen, right? As long as you go over, right? You've over allocated. It's going to pack up, and you may accidentally send extra data. But I think if you had like being wrong twice makes a right is what I'm kind of thinking here. Not best practice, and you could probably get into trouble on some other computer. But I think if you were to over allocate and over send data, and you probably end up seg faulting at some point, and then. I was thinking in between the two contiguous, like you're going to make a contiguous type of two chunks of data, right? So I was thinking internally between the two. But you could actually end up, because if the compiler added stuff in between, it probably added also at the last struct, right? And so you may be expecting to get a thing of length 8 or 7, but it could actually be of size 8, and you try to stuff it into memory that's only allocated to be size 7. And so you overwrote the bounds of memory, which could corrupt your program. And that actually happened to me in real life, and it was a nightmare to actually debug. So, well, I think if you have two contiguous structs, right, then it's fine, right? Because it's the same type of data if it's already contiguous, right? So it's safe in that sense. Oh, like how we had particles, but we had n particles, right? Right, but the compiler can actually add data into. So when you could actually ask size of, but the MPI actual when it under the library hood, right? Things can change. So I think you can get into trouble all the examples we were talking about where you could have these pitfalls. Now, specific examples, I cannot give you one right off the top of my head. We can try to derive one and see what happens on bridges.
I already had it escalated deterministic.
Okay. Yeah. Yeah. Okay. Yeah. I have no idea on the C standard. But yes, Eric's an excellent resource. Okay. We have our crazy data. Now we want to do a collective call, right? So a collective is all my ranks. We want to do a gather, for example. But we have these crazy data. We need to be able to provide, when you do an MPI collective, MPI sum operation, right? Well, we can't do that because our type is unknown to MPI. It's not a compiler, right? And so we have to tell it how do we actually operate on our custom pieces of data if we want to do a collective. So they give you the functionality to build your own operation. So in the code, one of the libraries I use is called pforce. It's for dynamic adaptive mesh refinement. In there's this these are actually used in real life codes, actually to build this up. So we're going to build a user function, which I'll show you. Then we got to tell it if the operations can commute, right? Is A plus B equal to B plus A? Or no, yes or no, does order matter? And then you store it in a custom handle, right? So for example, we can make a type contiguous of 7 doubles. I'm going to start into C type, commit it, yay, fun. And then we're going to make a custom operation. It's called stat, and we're going to pass in stats MPI func. It's commutative, that's what the 1 is down here, right? And then we're going to store it into op. And then how do we actually use this? We're going to pass in a bunch of these vectors, right? This is a memory array pointer, flat in, flat out. How many we're sending of the type vectors? Those are all 7 doubles, right? And then our actual custom operation. So with MPI stats, we need to pass this user function. What does it look like? Well, we kind of saw it has an input vector, an in-out vector, how many of the things we have, and what's the type. Okay, so here's the real function at the top. We're going to call it accumulate values func. Takes an input vector, and it has an in-out vector, so you can modify stuff. The length and the data type, right? So here, we're going to make up a kind of like a real vector, like velocity xyz. And then we're going to sum these values, okay, and stash it into our out vector, and then keep updating a pointer. Voila, fun, right? So that's how we actually do an accumulate example of our custom type, okay? And then finally, it's pretty easy, right? So you like initialize values and the sums, make your type, commit it, make your function, pass that in, and then you use the operation as we already saw. Okay. Overall, we just learned a whole bunch of derived data types, but what's the take-home message here? We saw these things got more and more complicated as we went up, the complexity tree. Overall, the more parameters you pass in, the more complex the MPI function is, the more expensive it is, right? So instead of just always using struct, which has unlimited, it's basically the most versatile of these derived data types, they are expensive in the sense that you have to pass so much more information. So you want to use the most basic type that you can that fits your bot, right? So again, performance of predefined using the intrinsic types. Those are built in. Contiguous, vector, index block, index, and struct. Okay. So, and then finally, as we just talked about, hierarchically construct these from the bottom up. Okay, finally, hands-on demo. You guys can code. We're actually somewhat on time. Wow. Okay, so 20 minutes. I'm going to pull up another slide deck. Let's see here. And FYI, all these lectures they're posted to the Moodle. And as you'll see, I actually have them on GitHub, so you can actually get all the originals. So there's a second slide deck I'll pull up, and we'll go quickly into the hands-on. Okay. All right. Hands-on. Everyone connect to bridges. Oh, you guys can't see this. Duplicate. Duplicate. Okay. So if you don't remember, SSH username at bridges2.psc.edu. We were having some connectivity issues earlier, but hopefully you guys can all get in. If you have questions, our hands-on helpers will definitely take a look. Yes. Oh, yeah. So Samir just volunteered to help everyone with these issues, okay? Okay, so get logged in. And then I put all exercises for the entire course in my home directory, which should be open. And you can just copy this whole exercises directory. I'll leave this up there, okay? Probably run into a break. Anyone have any questions so far? I know you're... Yeah. Yes, that is exactly what we were talking about, right? So you should make the most basic building blocks first, and you can keep constructing higher and higher, like more complex things. So you should construct with the most basic types first, and then keep adding to it. Yeah. So when you look at the slides again on like the first page when we introduced it, it looked like a tree, like a binary tree. Well, that's exactly what was happening, right? We were constructing, right? Yeah. Okay. Here, I'll come back to the slide, but I want to go over what the exercise is once we get there, and then the modules I have listed here. We'll come back. I'll put this back up shortly. And then today, inside of exercises, I put two scripts, interactive 8-day 1, which will automatically put you on the reservation that should be running and get you 8 cores. I think we reserved like 100 like 1,000 cores or something today. And then we'll just have a simple module load Intel MPI. The OpenMP one's being a pain. Okay, so this, if you're curious and you want to actually clone all these slides with the transition, the real PPTX things to explain, you can, and the exercises are there. Okay, so exercise 1, we're going to have a very simple, the A2D array, and then we're going to have 4 examples: contiguous, vector, indexed, instruct. And then inside of these programs, you'll see exercise 1 with each one of these, and then inside of those, there will be a to-do, but you'll see. Okay, so contiguous, I just want you to make a super simple, like contiguous, where you're gonna send, you'll see inside of the programs, like what you have to fill out. And it's essentially filling out count, old type, new type, and then it communicates, and then you can check against a reference to see if it's working, okay? So pretty trivial, right? You're sending contiguous chunks of data, voila, okay? And then vector again, right? You're gonna send vectors of data, right? So block, gap, regularly spaced intervals. And you're gonna have to fill out all the counts, blocks, and strides. And then indexed, right? With this one, it has chunks of data, right? And then it has an index, right? So here we want to send the data 6 through 9 and 13 and 14. It's a kind of a random data set, right? But then you need to say where the block counts. There's 2 chunks of data. How big are the block lengths? So the first one is 4. You'll have to make an array that says 4 and 2, right? And then finally, what's the displacements? Where does the first one start? That's 5 from the beginning. And then 12, right? In this example. So I pretty much just gave you the answers. Okay. And then create struct, right? So just a little bit. And then I cheated and I used the type extent. Don't kill me. But it's going to be on particles again. So we'll see that we have floats and then 2 ints on top. Okay? So to start, okay. I have these crazy timers. You'll watch these little dials disappear over 20-minute intervals. It's like voodoo magic, okay? I'll go back to the beginning. Do you guys, I'll put the things back up, but you see it's going, right? I spent way too much time on these slides, people. So little details. Yeah, too much time. Okay, so here it is again. Here's the instructions. So copy, right? Exercises, you just need to do this once for the entire program. And then for this one, we're going to go into exercises, exercise 1, derived data types. I was actually good, and if you're a Fortran programmer, this is the only exercise you get Fortran, but there's also C, right? So C and Fortran. And then if you grep or look in the files for each one of these, they'll have a to-do. So if you / to-do, then you'll see an instruction set, and it's literally like just a line for each one. And I left a gap of how many lines you have to fill in, okay? Inside of those, there's simple make files. After you've loaded Intel MPI with module load, which I'll show you again, you should just be able to type make. And then I think there's a run script in there, so you can do /run, and it should output something. And then from the inside of each one of these directories, there's a file called like expected output or output, right? So you can check to see if you implemented your program correct against the correct answer. Okay? And if you really get stuck, inside of right before here, I made a hidden directory. So a hidden directory just has a period at the beginning, so it doesn't show up with ls. But if you do ls-a, then you'll find a solution directory .soln. And then in there, that's where all the official answers are. Okay? Yes. So right now, just work. And then when you're done working, or if you want to take a break, you can do that too. So I stringed it together, so it's exercise, break, exercise, done for the day. So no more lecture. Thank you for bearing with me. So, okay? Does anyone want me to put it back on the first modules? Right? Okay. We're going to lose our timers, but that's okay. They do that. They're all fun. Okay, let me put it back to here. If you really want, you could just do a git clone of the original repository in this thing and instead of copy, but that works too. Okay.